December 15, 1932, Polish General Staff Headquarters, Warsaw. The cryptanalyst stopped writing mid-equation, his pencil hovering above a page dense with mathematical notation. Marian Rejewski, a 27-year-old mathematician from Poznan who had never worked in intelligence, had just seen something that shouldn't have been possible. The German military cipher machine, the Enigma, supposedly unbreakable by design, had a flaw. Not a weakness in the encryption itself, the mathematics behind Enigma's 159 quintillion possible settings remained sound. The flaw was structural, buried in the machine's wiring, invisible to anyone who didn't approach the problem as pure mathematics rather than cryptography. What Rejewski didn't know, what nobody in that room could have imagined, was that he had just solved the single most important intelligence problem of the coming war. Within 8 years, his discovery would allow Allied codebreakers to read Hitler's most secret communications in near real time. German U-boats would be hunted based on their own position reports. Wehrmacht divisions would walk into Allied ambushes because their orders had been intercepted and decrypted. The entire German intelligence apparatus would operate under the illusion of security while Allied commanders read their mail. The Germans called it Enigma, mystery. It would become the greatest intelligence failure in military history. Not because the machine was poorly designed, the Enigma was brilliantly engineered, based on sound cryptographic principles and manufactured with German precision. It failed because the Germans made a fundamental error. They assumed mathematics couldn't defeat engineering. They were wrong. This is the story of how 3 Polish mathematicians broke the unbreakable code, how British eccentrics turned that breakthrough into an industrial decryption operation, and how German confidence in mechanical security became their strategic blindness. One machine, 159 quintillion settings, broken by a 27-year-old who simply refused to accept that a cipher couldn't be solved. The Enigma machine emerged from the chaos of post-World War I Germany. Arthur Scherbius, a Berlin electrical engineer, patented his cipher machine in 1918, marketing it to banks, businesses, and governments as the solution to secure communications. The pitch was elegant, a portable encryption device that made messages impossible to decode, even if the machine itself was captured. By 1926, the German Navy had adopted it. By 1928, the German Army followed. By 1930, Enigma was standard equipment throughout German military and intelligence services. The device appeared deceptively simple, a wooden box roughly the size of a portable typewriter, weighing 26 pounds. Inside sat a keyboard, a lamp board displaying illuminated letters, and the machine's heart, 3 rotors, later expanded to 5, each containing internal wiring that scrambled electrical signals. The operator would type a message on the keyboard. Each keystroke sent an electrical pulse through the rotors, lighting up a letter on the lamp board. That letter was the encrypted output. The receiving operator, with an identically configured Enigma, would type the encrypted message, and the machine would display the original plaintext. The security came from the rotor system. Each rotor had 26 contact points representing the alphabet, wired internally in a scrambled pattern. When electricity passed through a rotor, it exited at a different angle than it entered. The signal then passed through the second rotor, scrambling again, then through the third rotor, scrambling a third time. The signal then hit a reflector, which sent it backwards through all 3 rotors again, scrambling in reverse. Finally, the lamp illuminated, showing the encrypted letter. The mathematical complexity was staggering. Each rotor could be set to any 26 starting positions. With 3 rotors, that meant 17,576 possible initial configurations. But the rotors could be installed in any order. 3 rotors could be arranged in 6 different sequences. That brought the total to 105,456 settings. Additionally, the rotors advanced with each keystroke, changing the encryption with every letter. After 66 keystrokes, the first rotor completed one revolution and advanced the second rotor one position. After 676 keystrokes, the second rotor completed a revolution and advanced the third. The entire sequence repeated every 16,900 keystrokes. The Germans added a plug board, a panel with cables that could swap letter pairs before encryption. With 10 cables swapping 20 letters, the plug board alone contributed 150 trillion possible configurations. Multiply that by the rotor settings, and the total reached approximately 159 quintillion possible keys, a number written as 159 followed by 18 zeros. The Germans calculated that even if an enemy captured an enigma and knew the general system, breaking a message without knowing that day's specific settings would require testing every possible configuration. At one setting per second, testing all possibilities would take longer than the age of the universe. The cipher was mathematically impossible through brute force. Therefore, the Germans concluded it was impossible, period. They were catastrophically wrong, not because the mathematics were incorrect. Brute force was indeed impossible. They were wrong because they forgot that mathematics could approach the problem differently. Polish intelligence faced enigma first. Poland, sandwiched between Germany and the Soviet Union, understood that the next war would begin with a German invasion. Reading German military communications was an existential necessity. In 1928, when Germany began deploying Enigma to military units, Polish intelligence obtained access to a commercial version of the machine purchased before military modifications were implemented. The commercial Enigma revealed the basic mechanical principles but lacked the plug board and used different internal wiring. It was enough to understand the system, but not enough to break military messages. For 3 years, Polish cryptanalysts attacked Enigma using traditional linguistic methods. They searched for cribs, known or guessed plaintext that might appear in encrypted messages. They analyzed letter frequency, looking for statistical patterns. They built tables of common German military phrases. Nothing worked. The rotor system destroyed all traditional cryptanalytic techniques. Letter frequencies meant nothing when the cipher changed with every keystroke. Cribs were useless without knowing the rotor settings. Pattern analysis failed because patterns didn't exist. By 1931, Polish intelligence concluded that linguists couldn't break Enigma. The Cipher Bureau, led by Major Guido Langer and his deputy Captain Maximilian Chiensky, made a radical decision. They would recruit mathematicians instead of linguists, treating Enigma as a mathematical problem rather than a linguistic cipher. In September 1932, Poznan University mathematics professor Zdzisław Krygowski recommended 3 of his former students, Marian Rejewski, Henryk Zygalski, and Jerzy Różycki. All 3 were in their mid-20s, recent graduates with no military experience and minimal knowledge of cryptography. They were hired not despite their lack of traditional qualifications, but because of it. Traditional cryptanalysts had failed. The Cipher Bureau needed people who thought differently. Marian Rejewski received the assignment. He was given everything Polish intelligence had collected on Enigma, detailed photographs of the commercial machine, intercepted military messages, observations about message formats and procedures. He was told the problem was considered unsolvable. He was given an office in the Cipher Bureau headquarters, a stack of blank paper, and instructions to try anyway. Rejewski began not with the encrypted messages, but with the mathematics of permutations. The Enigma was fundamentally a permutation cipher. Each rotor configuration created a specific mathematical permutation, a rearrangement of the alphabet. The encryption process was applying one permutation, then another, then reversing through them all. If Rejewski could determine the mathematical properties of those permutations, perhaps he could work backwards from intercepted messages to deduce the rotor settings. The problem seemed impossible.
To determine permutations, he needed to know how the rotors were wired internally. The Germans considered this their most closely guarded secret. Each rotor's internal wiring pattern was classified information, changed irregularly, and known only to authorized personnel. Without that wiring diagram, Rejewski couldn't build the mathematical model he needed. Then, in December 1932, French intelligence delivered a gift that would change the war. Captain Gustave Bertrand of the French Deuxième Bureau had cultivated a German intelligence source codenamed Asche, later identified as Hans Thilo Schmidt, a cypher clerk in the German Defense Ministry. Schmidt, motivated by financial difficulties and resentment toward his employers, provided Bertrand with documents including instructions for Enigma operation and, critically, the wiring specifications for the 3 military rotors being used in 1932. Bertrand offered this intelligence to British and French cryptanalysts. Both rejected it. Without captured Enigma machines to test against, the wiring diagrams seemed useless. Bertrand sent copies to Polish intelligence as a courtesy. The Poles understood immediately what they had. The wiring diagrams gave Rejewski the mathematical foundation he needed. On December 15, 1932, Rejewski sat down with the wiring specifications and began building his equations. The mathematics were elegant and brutal. Rejewski represented each rotor as a permutation function. The complete Enigma encryption process could be expressed as a series of function compositions, mathematical operations stacked on top of each other. By analyzing intercepted messages, particularly the message keys transmitted at the beginning of each message, Rejewski could observe the effects of these permutations without knowing the initial rotor positions. The breakthrough came from a security flaw in German operating procedures. To prevent errors, German operators transmitted each message key twice. If the actual message began with rotor settings XYZ, the operator would first set the rotors to the daily starting position, type XYZ, XYZ, then reset the rotors to XYZ and type the actual message. This 6-letter preamble, transmitted with every message, gave Rejewski the data he needed. Because the same 3 letters were typed twice, Rejewski could observe relationships between the first and fourth letter, the second and fifth letter, and the third and sixth letter. These relationships revealed the permutation structure. Over hundreds of intercepted messages, patterns emerged. By January 1933, Rejewski had constructed a set of equations describing Enigma's internal structure. By late January 1933, he had solved those equations. By early February 1933, he had successfully decrypted his first German military message. The Poles had broken Enigma, not through espionage, not by capturing codebooks, but through pure mathematics applied to an engineering problem. The Germans never suspected. They remained confident that mathematical security made Enigma invulnerable. But breaking Enigma once didn't mean breaking it operationally. The Germans changed rotor settings daily, selected from codebooks distributed monthly to all Enigma users. Each day at midnight, every German military Enigma machine in the world switched to new settings. Yesterday's breakthrough was worthless today. Rejewski had proven Enigma could be broken, but breaking it daily, fast enough for intelligence to be useful, required something more than equations on paper. Rejewski, working with Rejitsky and Zygalski, developed mechanical aids. The first was the cyclometer, a device using 2 Enigma machines connected electrically to test rotor combinations rapidly. Then came the card catalog, not actually cards, but sheets listing rotor positions that produced specific permutation patterns. With these tools, Polish cryptanalysts could determine daily settings in hours rather than weeks. By 1938, the Polish Cypher Bureau was reading German military communications routinely, providing Polish intelligence with strategic warning of German intentions. Then, in September 1938, the Germans upgraded Enigma security. The number of rotors increased from 3 to 5, chosen from 8 available rotors. The plug board was enhanced to swap more letters. The mathematical complexity increased by orders of magnitude. Rejewski's card catalog became obsolete overnight. The cyclometer method still worked theoretically, but would require 60 times more equipment and personnel to handle the expanded rotor selections. The Poles responded with their masterpiece, the bomba cryptologiczna, cryptologic bomb. The name came not from explosive devices, but from the ticking sound the machines made during operation. Each bomba consisted of 6 Enigma machines mechanically connected, testing rotor settings in parallel. The device automated the mathematical analysis Rejewski had performed manually, cycling through possibilities at mechanical speed. With 6 bombas operating simultaneously, the Poles could test all possible rotor orders and positions in approximately 2 hours. By November 1938, the Polish Cypher Bureau had constructed 6 bombas and was breaking Enigma daily again. But Polish intelligence understood the strategic picture was deteriorating. Germany was rearming aggressively. War was coming. Poland would need allies. On July 25, 1939, 5 weeks before Germany invaded Poland, Polish intelligence held a secret meeting in the Kabaty Woods outside Warsaw. Representatives from British and French intelligence services were invited. Major Langer and Captain Chiewski explained what the Poles had accomplished. They demonstrated the bomba. They provided complete technical documentation. They gave the British and French working replicas of the Polish Enigma reconstruction. The British were stunned. Their government code and cipher school at Bletchley Park had been working on Enigma since 1938 with minimal success. The revelation that Polish mathematicians had been reading German military communications for 6 years, using mechanical devices to break what the British considered unbreakable, fundamentally changed Allied intelligence capabilities. But there was little time to exploit this gift. On September 1, 1939, Germany invaded Poland. On September 17, the Soviet Union invaded from the east. Polish intelligence evacuated. Rejewski, Rzycki, and Zygalski escaped to Romania, then to France, bringing their knowledge to Allied cryptanalysis efforts. At Bletchley Park, British mathematician Alan Turing took the Polish techniques and expanded them for industrial-scale code breaking. Turing understood immediately what Rejewski had discovered, that Enigma was vulnerable to mathematical attack exploiting its own internal structure. But British codebreakers faced challenges the Poles hadn't encountered. German military communication security had improved. The number of daily messages had increased dramatically. The Germans introduced procedural changes that eliminated some of the vulnerabilities Rejewski had exploited. Most significantly, the German Navy used a 4-rotor Enigma variant that was completely impervious to Polish methods. Turing's solution was the bomb, named after the Polish bomba, but far more sophisticated. Turing's bomb exploited a different Enigma vulnerability, the reflector. Because Enigma used a reflector to send signals backwards through the rotors, the machine had a reciprocal property. If letter A encrypted to letter Q, then letter Q encrypted to letter A at the same rotor position. This seems like a minor detail. It was actually a catastrophic flaw. Turing realized that if you knew even a fragment of plain text, a crib, and could align it with the encrypted message, you could use the reciprocal property to test rotor settings. The bomb would try settings until it found one that produced the known crib without any letter encrypting to itself. Because Enigma's reflector guaranteed no letter ever encrypted to itself, any rotor setting that produced A encrypting to A could be eliminated immediately. The first bomb became operational at Bletchley Park in March 1940. By August 1940, it was routinely breaking Luftwaffe Enigma keys. By 1941, improved bombas were tackling Wehrmacht and SS messages. By 1942, after capturing Enigma materials from U-boat 110, British cryptanalysts had broken the 4-rotor naval Enigma. At peak production, over 200 bombs worked around the clock at Bletchley Park and outlying stations, processing thousands of intercepted messages daily. The operational impact was immediate and devastating. German commanders communicated, believing their messages were secure. Luftwaffe formations received orders via Enigma. U-boat wolf packs were vectored toward convoys by encrypted commands. Wehrmacht division movements were coordinated through Enigma traffic. All of it was being read by Allied intelligence, sometimes within hours of transmission. The intelligence product was codenamed Ultra, classified above top secret. Distribution was strictly controlled. Only senior commanders with special clearance received Ultra intelligence, and only in a sanitized form that concealed the source. Elaborate cover stories were maintained. If Ultra revealed a U-boat position, the Royal Navy would send a reconnaissance aircraft to locate the submarine before attacking, giving the Germans a plausible reason for the subsequent sinking that didn't involve compromised communications. The Battle of the Atlantic demonstrated Ultra's power. German U-boats operated in coordinated wolf packs, controlled from headquarters via Enigma signals. British naval intelligence, reading these orders, could route convoys away from waiting submarines. When Admiral Karl Dönitz positioned his U-boats across convoy routes, Allied commanders knew their locations before the submarines knew the convoys were coming. Merchant ship losses, which had threatened to starve Britain into surrender in 1941 and 1942, declined precipitously once naval enigma was broken. By 1943, the U-boats were being hunted systematically, their positions betrayed by their own communications. The invasion of Normandy depended heavily on ultra-intelligence. Allied planners read German assessments of where they expected the invasion, which units were deployed where, and how quickly reinforcements could respond. The elaborate deception operation, convincing the Germans that Normandy was a feint and Calais was the real target, was validated through Enigma decrypts showing German commanders believed the deception. When Allied forces landed on June 6, 1944, German confusion about Allied intentions was confirmed by intercepted Enigma messages showing Hitler's headquarters debating whether to release armored reserves to Normandy or hold them near Calais for the real invasion. Throughout 1944 and into 1945, Ultra provided strategic and tactical intelligence that shortened the war by months, possibly years. Soviet offensives coordinated with Western advances based partly on intelligence about German dispositions that Ultra revealed. German counteroffensives, like the Battle of the Bulge in December 1944, were detected through Enigma traffic, though not quickly enough to prevent the initial assault. The systematic destruction of German infrastructure, oil refineries, rail yards, aircraft factories, was targeted using intelligence from decrypted German damage reports and resupply requests. Yet through all of this, the Germans never suspected Enigma was compromised. They attributed Allied success to superior resources, espionage networks, traffic analysis, or bad luck. They never considered that their unbreakable cipher machine might have been broken mathematically. German cryptographic authorities reviewed Enigma security repeatedly throughout the war. Each time, they concluded the system was sound. The mathematics guaranteed security. Therefore, security existed. This confidence persisted despite mounting evidence. When U-boat positions were compromised repeatedly, German naval intelligence investigated. They considered every possibility except the correct one. Were there traitors in headquarters? Were the Allies using new radar systems? Had they broken other, older codes? The investigation concluded that security procedures were inadequate. Operators were not changing settings often enough. Messages contained stereotyped phrases, and cribs were being provided inadvertently. They never questioned whether the mathematics itself could be defeated. Admiral Dönitz, commanding the U-boat force, received a report in 1943 analyzing whether Enigma might be compromised. The report, prepared by mathematicians and cryptographers, concluded definitively that breaking Enigma without captured materials was impossible. The number of possible settings exceeded what any conceivable code-breaking operation could test. Even with captured machines, breaking messages without the daily settings would require computational resources that didn't exist. The report recommended continuing Enigma use with enhanced operational security. This recommendation condemned thousands of German servicemen to death based on faulty assumptions about what mathematics could accomplish. The faulty assumption was fundamental. German engineers designed Enigma and proved mathematically that brute force attacks were impossible. They concluded this made the system secure. But Rejewski, Turing, and the teams at Bletchley Park weren't using brute force. They were exploiting mathematical properties of the permutation system itself, finding shortcuts through the mathematical space that brute force would have to search exhaustively. The Germans had designed an engineering marvel and proven it mathematically sound, but they hadn't proven it was immune to mathematical analysis from unconventional angles. One specific incident illustrated German blindness perfectly. In 1942, British forces in North Africa captured a German signals unit intact, including Enigma machines, codebooks, and daily settings for the next month. British intelligence immediately began reading Afrika Korps communications with complete clarity. Field Marshal Erwin Rommel's supply convoys were intercepted based on his own status reports. His tank formations walked into ambushes because Allied commanders knew his plans before his subordinates did. Rommel repeatedly complained that the enemy seemed to anticipate his every move, suggesting British intelligence had penetrated German communications. German headquarters investigated. They confirmed that the captured unit had possessed current Enigma materials. They implemented an emergency change of procedures and settings. Then they concluded the investigation. The new settings were secure because the mathematics remained sound. They never considered that the capture had given British cryptanalysts insight into procedures and message formats that made breaking subsequent messages easier. They changed the lock, but didn't consider whether the entire security architecture was flawed. British codebreakers faced one persistent problem that threatened the entire Ultra operation. The German Navy's four-rotor Enigma used exclusively for U-boat communications. The fourth rotor, added in February 1942, exponentially increased complexity. The three-rotor bombs couldn't handle it. For 10 months in 1942, British naval intelligence was blind. U-boat sinkings of Allied shipping increased catastrophically. The Battle of the Atlantic reached its crisis point. Then, on October 30, 1942, destroyer HMS Petard depth-charged U-559 in the Mediterranean. As the submarine sank, 3 British sailors, Lieutenant Anthony Fasson, able seaman Colin Grazier, and 16-year-old canteen assistant Tommy Brown, boarded the stricken vessel and retrieved Enigma codebooks before the submarine went down. Fasson and Grazier drowned when U-559 sank suddenly. Brown survived, clutching the codebooks. The materials he recovered gave Bletchley Park the foundation for breaking the four-rotor naval Enigma. By December 1942, naval messages were being decrypted again. U-boat losses resumed their upward trajectory. Fasson and Grazier received posthumous George Crosses. Their sacrifice had reopened the intelligence window into U-boat operations. The technical evolution of code-breaking machinery accelerated throughout the war. The bombs, while effective, were electromechanical devices, limited by the speed of rotating drums and mechanical relays. In 1943, Bletchley Park engineer Tommy Flowers proposed a radical solution: electronic computation using vacuum tubes. Flowers designed Colossus, the world's first programmable electronic digital computer, specifically to break Lorenz cipher machines used for high-level German communications. Colossus became operational in February 1944, processing calculations at speeds unimaginable with mechanical systems. Though designed for Lorenz rather than Enigma, Colossus represented the conceptual leap from mechanical code-breaking to electronic computing. Modern computer science traces its origins directly to the cryptolytic challenges of World War II. At its peak in 1945, the Bletchley Park operation employed over 9,000 personnel. The vast majority were women: WRNS operators running bombs, clerks processing intercepts, translators rendering decrypted German into English intelligence reports. The work was tedious, repetitive, and absolutely secret. Operators worked 8-hour shifts running bomb cycles, watching for stops that indicated a possible rotor setting had been found. They had no idea what messages they were decrypting or how the intelligence was being used. Security was so strict that different sections of Bletchley Park worked in isolation, each knowing only their specific function. The bomb operators didn't interact with the analysts who interpreted the decrypts. The analysts didn't know how the messages were being broken. Information flowed only upward, never laterally. This compartmentalization created absurd situations. Gordon Welchman, mathematician responsible for improving bomb design and managing the Enigma code-breaking operation, later wrote that he discovered in 1941 that another team at Bletchley Park was working on the same problem using different methods. Neither team had been told the other existed. Cooperation would have accelerated progress by months. But security considerations overrode efficiency. The risk that one person knowing too much might compromise the entire operation was considered more dangerous than the inefficiency of redundant work. The human cost of maintaining ultra-security was occasionally severe. Allied commanders sometimes had to allow German attacks to proceed, even when Ultra had provided a warning, because responding would reveal the intelligence source. Coventry, bombed by the Luftwaffe on November 14, 1940, became legendary in this regard. Intelligence officials knew the raid was coming, but allegedly chose not to evacuate civilians or reinforce defenses excessively because the Germans might deduce that Enigma was compromised. Post-war research has challenged this narrative. Evidence suggests the intelligence was ambiguous about the specific target, but the principle was real. Ultra-intelligence was so valuable that protecting the source sometimes required accepting tactical losses to preserve strategic advantage. The ethical implications troubled some participants. Knowing that information could save lives, but being forbidden to act on it, created moral anguish. One Bletchley Park analyst later described reading decrypted reports of Wehrmacht units massacring civilians in Eastern Europe. The information couldn't be shared because revealing it would expose the intelligence source. Thousands died while Allied intelligence possessed detailed knowledge of German atrocities, but couldn't use that knowledge without compromising capabilities that might save even more lives later. The abstract mathematics that Rejewski manipulated in 1932 led directly to life-and-death decisions made by commanders who weighed intelligence value against operational security and human lives. German cryptographers, unaware their system was broken, continued to improve Enigma throughout the war. They introduced new rotor designs, modified reflector wiring, and implemented more complex plug board configurations. Each change temporarily disrupted Allied code breaking until new procedures and techniques were adapted. But the fundamental mathematical vulnerability remained. Enigma's permutation structure, the reciprocal property from the reflector, the cribs that German operating procedures provided, these couldn't be eliminated without completely redesigning the system. A complete redesign was impossible for an organization that had deployed hundreds of thousands of Enigma machines to units across Europe, North Africa, and at sea. The Germans were trapped by their own logistical success. Enigma worked brilliantly for its intended purpose, providing encrypted tactical communications in the field. Machines were robust, portable, and relatively easy to operate. Messages could be encrypted and decrypted quickly. The system scaled to support an entire military apparatus. Replacing it with something new would require manufacturing hundreds of thousands of new machines, distributing them worldwide, retraining tens of thousands of operators, and accepting a transition period of vulnerability. The organizational inertia was insurmountable. So Enigma continued even as evidence mounted that security was compromised somehow. In May 1945, Germany surrendered. Allied and American forces occupied Germany, seizing intelligence files, interrogating personnel, and securing communications equipment. The full scale of Enigma deployment became apparent. Over 200,000 machines produced, used by every branch of German military and numerous government agencies. In the chaos of defeat, German cryptographic authorities still believed Enigma was secure. They attributed their defeat to material inferiority, strategic errors, and overwhelming Allied resources. The possibility that their communications had been read throughout the war never seriously occurred to them.
Allied authorities maintained strict secrecy about Ultra. The full story of Enigma code-breaking remained classified until the 1970s. Captured Enigma machines were distributed to former colonies and friendly nations who continued using them, unaware that Britain and the United States could read every message. The existence of Colossus was concealed, the machines were dismantled, the designs classified, and the pioneering work in electronic computing remained secret for decades. Personnel who had worked at Bletchley Park were forbidden from discussing their wartime duties, sometimes even with spouses and family. This secrecy served multiple purposes. It protected intelligence sources and methods that remained relevant in the Cold War. It concealed the extent to which Allied victory had depended on compromised German communications, maintaining the narrative of strategic and material superiority. And it prevented the Soviets, who had received some Enigma intelligence during the war but not the full Ultra capability, from understanding exactly what Britain and America had achieved. The secrecy also meant that Marian Rejewski, the man who had broken Enigma in 1932, received almost no recognition for his achievement. He survived the war working for Polish intelligence in exile, then returned to Communist Poland in 1946. He worked as an accountant for a cable factory. His wartime cryptanalytic work was classified and unacknowledged. Only in the 1970s, after British disclosure of Ultra, did Rejewski's role become public. He was 72 years old when he finally received recognition for the work he had completed at age 27. He died in 1980, having spent most of his life in obscurity while the system he had broken became legendary. Alan Turing faced a different tragedy. His work at Bletchley Park remained classified after the war. He couldn't discuss his greatest achievements. He continued mathematical research, developing theories of computation and artificial intelligence that anticipated modern computer science by decades. In 1952, he was prosecuted for homosexuality, then illegal in Britain. Convicted and subjected to chemical castration as an alternative to imprisonment, Turing died in 1954 from cyanide poisoning, officially ruled a suicide, though some evidence suggests accidental death. He was 41 years old. The British government formally apologized in 2009, 55 years after his death.
The human price of the mathematical war extended beyond the battlefield. Those who fought it often paid in silence, forbidden from acknowledging their contributions, their achievements classified into obscurity. Rejewski worked in an accounting office. Turing died in disgrace. Thousands of Bletchley Park personnel returned to civilian life unable to explain what they had done during the war, their role in shortening the conflict permanently secret. Modern analysis estimates that ultra-intelligence shortened the European war by 2 to 4 years. Eisenhower stated after the war that Ultra had been decisive, saving countless lives. German strategic options were constrained throughout 1943-1945 by Allied knowledge of their dispositions and intentions. The Battle of the Atlantic, which might have starved Britain into negotiating peace, was won partly through knowledge of U-boat positions. The invasion of Normandy succeeded partly because Allied planners knew German expectations and dispositions. The systematic destruction of the German war industry was targeted using decrypted damage reports and resupply requests. 2 to 4 years shortened, millions of lives saved, cities spared from additional bombing, concentration camps were liberated earlier, the Holocaust was curtailed sooner. All because a 27-year-old Polish mathematician looked at an unbreakable code and decided to treat it as a mathematical problem rather than a linguistic cipher. The Enigma machine, a marvel of German engineering, mathematically sound, operationally robust, was defeated not by better engineering, but by better mathematics. The Germans built an excellent system based on solid principles. They proved it was secure against every attack they could imagine, but they couldn't imagine Marian Rejewski. At the Imperial War Museum in London, an Enigma machine sits in a display case, 3 rotors visible through the open lid, the plug board's cables frozen in a meaningless configuration. The placard describes it as the cipher machine that lost the war. This is historical oversimplification. The Germans didn't lose because of Enigma. They lost because of strategic overreach, material inferiority, and tactical errors compounded over 6 years of war. But Enigma broke their command structure, exposed their planning, turned their communications network into an Allied intelligence stream. The machine didn't lose the war by itself. It made losing inevitable. The irony that haunts the Enigma story is that the machine worked exactly as designed. The encryption was mathematically sound. The engineering was excellent. German procedures, while not perfect, were generally adequate. The system failed because the Germans made a philosophical error. They confused mathematical possibility with practical security. They proved that brute force couldn't break Enigma and concluded this made it unbreakable. They never considered that mathematics might approach the problem laterally, that structure itself could be weakness, that clever analysis might find paths through the mathematical space without searching exhaustively. This error, this fundamental misunderstanding of what mathematics could accomplish, cost Germany the war, not immediately, not obviously, but systematically, day by day, message by message, as Allied commanders read German plans and positioned forces accordingly. The Germans fought blind while the Allies read their mail. No amount of courage, tactical brilliance, or operational skill could overcome that disadvantage. In mathematics departments today, Enigma is taught as a case study in the difference between theoretical security and practical security. The machine's design was theoretically secure, the mathematics were sound, the key space was large enough to defeat brute force, but theoretical security assumes perfect implementation, perfect procedures, and no clutter analysis. Real-world systems face imperfect implementation, human operators who make mistakes, and adversaries who think creatively. Enigma fell not because the theory was wrong, but because the real-world implementation provided openings that brilliant minds could exploit.
Marian Rejewski, sitting in Warsaw in December 1932, couldn't have known that his equations would contribute to Allied victory 13 years later.
He was solving an intellectual puzzle, applying mathematical techniques to a cryptographic problem because traditional methods had failed. The fact that his solution would enable industrial-scale intelligence operations, inform strategic decisions, and help win the war was beyond his knowledge or intention. He was doing mathematics. The rest followed. That's the haunting lesson of Enigma, that an abstract mathematical problem solved in obscurity could cascade into strategic consequences, that a cipher machine deployed in the 1920s for commercial communications could become a military vulnerability in the 1940s. Assumptions about security based on mathematical proofs could be correct in theory, but fatal in practice. That the war was won partly through differential equations, permutation theory, and mechanical calculators operated by people who didn't know what they were accomplishing. The death ray that failed, the particle beams that never worked, the exotic physics that promised to change warfare, none of it mattered. The weapon that actually changed the war was mathematics applied to cryptography by people, most of whom never fired a shot. The thunder wasn't from machine guns or bombs. It was the mechanical clicking of rotors testing rotor positions, the quiet scratch of pencils working through permutations, the whisper of intelligence reports typed on secure typewriters in basement offices where secrets were kept by people who would carry them silently for decades. Enigma was supposed to be unbreakable. The mathematics proved it. The engineering confirmed it. The Germans believed it. They were wrong. Not because they were stupid or incompetent, but because they assumed mathematics had limits that it didn't. One Polish mathematician refused to accept those limits. Then a British mathematician built industrial processes around that refusal. Together, they broke the unbreakable, read the unreadable, and turned German security into German blindness. 159 quintillion possible settings, broken by a 27-year-old with equations on paper. The impossible made routine by machines testing settings at mechanical speed. Hitler's spy network was outwitted not by better spies, but by better mathematics. The greatest intelligence coup of World War II was accomplished by people who couldn't talk about it for 30 years after it ended. The Enigma machines continued clicking through the war, encrypting messages, providing illusory security, functioning perfectly while betraying every secret they were designed to protect. German operators never knew. German commanders never suspected. They lost the war still believing their communications were secure. The machine that was supposed to make messages unreadable made Germany transparent, and the Allies, reading everything, said nothing until long after victory was safe and the secret no longer mattered. Mathematics defeated engineering. Patience defeated confidence. Silence defeated the machine that was supposed to beat everyone. The impossible code was broken because someone decided impossible just meant not yet solved. The spy network was outwitted because someone learned to read their mail. And the war was shortened by years because a farmer's son from Poznan who loved mathematics saw patterns in permutations that German engineers had assumed couldn't exist. The thunder of breaking Enigma was silent, but it echoed through every German defeat, every intercepted convoy, every ambush based on red communications, a silent thunder that drowned out the mechanical clicking of rotors and exposed the fatal difference between mathematical theory and strategic reality. The code that couldn't be broken was broken daily, and Germany lost the war partly because it never knew.